and then it will sort of be the focus of the talk in some way. But I want to talk about the local geometry of rank 2 distributions, in particular Cartan prolongations, the symplectification procedure for rank 2 distributions, and then the existence of normal Cartan connections on some of these structures. So let's get going. So firstly, I'll introduce how we get normal Cartan connections in the context of Tanaka theory. And then I want to give a very brief summary of the symplectification procedure for rank 2 distributions that Dr. Dubrov and Dr. Zelenko developed. I'll really miss a lot of details in that. It'll sort of be an excessively brief summary of a pretty complicated thing, but we'll accept it mostly as a black box here. And then I want to give some other perspective on this symplectification procedure via Cartan prolongations, which is a little more classical. So the idea is we're going to have the symplectification procedure. I mean, we'll start with a rank 2 distribution, and the symplectification procedure will give us a new rank 2 distribution on a higher dimensional manifold. And Cartan prolongations, if we take a bunch of Cartan prolongations, we'll locally get back the symplectification procedure. So it'll be the result of iterated Cartan prolongations. And then really the main point of the talk, the main focus is going to be on which of these intermediate geometries that we get from prior Cartan prolongations, on which of those do normal Cartan connections exist. So that's a brief summary, but hopefully things will become more clear as I go along. Also, how long, what should I aim for time? Sorry, I should have asked.
So the plan was 30 minutes, so...
Whatever, we'll see how long it goes, I guess. I won't go long, I promise. So we're going to start with a distribution on some smooth manifold, and we'll take the weak derived flag of this thing and label it negatively. So at each point, d negative I is just, the previous one, d negative I plus 1, plus brackets with d. And this weak derived flag hopefully gives a filtration of the tangent bundle. I mean, hopefully d negative mu is actually the tangent space. And in that case, we can define the Tanaka symbol m to be sort of the associated graded object to that filtration, right? And at least in the case that it's equivariant, that is, at least in the case that these things are like actually distributions in themselves of constant rank, we get the Tanaka symbol is a Lie algebra. So it's a Lie algebra which is negatively graded. The bracket, is just coming from brackets of vector fields. It turns out it's well defined up to the modulus. And so we get this negatively graded fundamental Lie algebra. And we can perform some purely algebraic procedure on this thing that's called the Tanaka prolongation, the algebraic Tanaka prolongation, and prolong it to a graded Lie algebra. So these other pieces come from the prolongation, the positive pieces, and possibly the zero piece. So that's our Tanaka symbol, and our M is the Tanaka symbol, and G is its prolongation here. We have G as an M module, so we can talk about the Lie algebra cohomology with coefficients in G. And indeed, it's graded because M and G are both graded, so the cochain modules are graded, and we can just think about the positive part of that cochain complex. And the coboundary map is sort of very easy to write down, at least for the one cochains, and this is the only one that we'll care about for the sake of this talk, so I thought I'd just write it down explicitly, but the point is just that it's very easy to write down. And once we have this coboundary map, we can talk about G plus invariant normalization conditions. So a G plus invariant normalization condition here is just a complement to the image of the coboundary map in each graded piece, which is, as the name suggests, G plus invariant, right? So all I'm going to just, every time I say G plus invariant normalization condition, just think complement to the image of the coboundary map. That's what I mean, right? And once we have our G plus invariant normalization condition, it turns our Tanaka bundle, if you know what that is, it's a bundle that you get over your manifold. It turns this thing not just into a G plus bundle, but actually into a normal Cartan connection. So the curvatures of our Cartan connection are going to live in our normalization condition N. And again, there's probably a lot of details obscured here that some of you are probably very aware of, and others of you maybe are not, and that's okay. But for the rest of the talk, what I'm going to be interested in mostly is finding normalization conditions so we get Cartan connections on the Tanaka bundles for our distribution. Okay, so before I give a summary of the symplectification procedure of Dubrov and Zelenko, I'd like to fix notation for a certain algebra. So I'll be using h, x, e, and y for GL2, and y, h, and x are going to be an SL2 triple in that. And then epsilons and eta will denote the Heisenberg algebra. And the algebra that's going to kind of keep coming up over and over again in this talk is going to be GL2 acting on acting on the Heisenberg algebra, where SL2 acts irreducibly on these epsilons. So it's a semi-direct product where SL2 acts irreducibly on these epsilons. And I'm going to call this the symplectic symbol, maybe, or the symplectic algebra, or something like this. You'll see why in a bit, I guess. So, a brief summary of the symplectification procedure here. We're going to start with a rank 2 distribution on an n-dimensional manifold, and we'll add a sort of a very weak assumption that this thing is of maximal class. I won't define clearly what that is. It means that some osculating flag is complete. Really, the main point is that the germs of maximal class are generic. And in fact, in low dimensions, all are of maximal class. But we start with some weak assumption on D here. And we can take from D the annihilator of D2 in the cotangent bundle, which is just the covectors that annihilate the second piece of this weak derived flag, right, and take away the annihilator of D3. And on some open dense subset of this set, we're going to lift our distribution, right? We're going to lift D to a distribution on RD, which is this open dense subset. And using some sort of black box osculation procedure, we're going to actually get a rank 2 distribution on the projectivization of RD. So RD is subset of this cotangent bundle, this linear in the fibers, and so we can quotient out by Euler vector fields here, right? We can projectivize in each fiber. And so from our rank 2 distribution on an n-dimensional manifold, we've now gotten a rank 2 distribution on a 2n minus 4 dimensional manifold here. And you might say, why do we want to do this? Why do we want a different rank 2 distribution than the one we started with? Well, this isn't just any rank 2 distribution. It has some very nice special properties. For one, the constant, the Tanaka symbol of E is actually constant already and independent of the original distribution. So our constant Tanaka symbol is actually the algebra that I introduced before, the symplectic algebra, right? And maybe it's worthwhile to note the grading here that epsilon 1 has weight -1 here, so this is 3-dimensional G plus. When you prolong, I guess, you get the entire symplectic algebra. You start with a subalgebra of it for the symbol. But remember, we're interested in finding G plus invariant normalization conditions, right? We want to find Cartan connections for these Tanaka bundles, and G plus here is relatively small, right? So maybe it's not surprising that there's actually a normal Cartan connection on this for this algebra. In particular, what I mean by that, again, is that I can find a G plus invariant complement to the image of the co-boundary map, right?
Sorry, Nicklas,
yeah.
just ask your notation. So I mean, you have E inside the inside the GL2, but you're also referring to E up there. Is that?
Yeah. E where? Sorry.
E has constant Tanaka symbol. Can you just go back?
Yeah. Sorry. I should. That's poor notation. So E up here is the new distribution. I don't know why I chose that notation. Yeah. So the result of the symplectification procedure, the new rank 2 distribution I'm referring to is E, but then also this is an element of GL2.
Yeah, that's rank.
This is 2n minus 4. E is.
Okay.
E is rank 2. Yeah. Sorry. Okay. So why is the symplectic symbol nicer than the Tanaka symbol? Well, for one thing, what I just said, like a normalization condition always exists for the symplectic symbol, right? We can sort of do that universally, which is very nice. So we have a normal Cartan connection on this new distribution, but that's definitely not true for Tanaka symbols, for the Tanaka bundles in general. In fact, locally, the Tanaka symbol is not usually even constant, so you really can't even ask that question a lot of the time. For n greater than or equal to 8, Tanaka symbols are not generically constant. On the other hand, the symplectic symbol is, constant not just for an individual distribution, but for every distribution, right? So this is sort of much better. Okay, so like the main idea that I want to convey and then ask questions about is that this symplectification procedure is the result of iterated Cartan prolongations, okay? And so we're going to get some prior Cartan prolongations. So we're going to get some intermediate geometry between these two, between the initial distribution and the symplectified distribution. And we want to ask which of those intermediate geometries have constant Tanaka symbol. So when is the Tanaka symbol of some number of Cartan prolongations independent of the original distribution? And then further, when do we get a normal Cartan connection? Is it on the second Cartan prolongation, or is it on the last one? We know they exist once we arrive at the symplectic symbol. So we know eventually this happens, but it might happen prior to the symplectic symbol. Feel free to stop me and ask questions, by the way. I was aiming for 25 minutes, so hopefully we'll see. Okay, so I should introduce what Cartan prolongations are. It's maybe a little more classical than the symplectification procedure. I think it's a pretty natural construction, but it might not be completely transparent. If we have a rank 2 distribution on a smooth n-dimensional manifold, the Cartan prolongation, which I'll denote per prolongation of D, is a new rank 2 distribution over the fiber-wise projectivization of D. So again, we're just factoring out by Euler vector fields, right? This is one dimension higher because it's a rank 2 distribution than the original manifold. And we define it to be the distribution whose fiber over a line L is just the vectors that project down to that fiber. So it's sort of a tautological construction in a way. It seems very natural. Why does it deserve the name of prolongation? Well, if you take horizontal curves with respect to your original distribution, you can sort of prolong those naturally to PD by taking their tangent line, right? So if I have a curve that's horizontal, its tangent line is in the distribution, so I can lift it naturally, and it gives me a new curve in PD that's horizontal to the Cartan prolongation. And two of these things agree if and only if their tangent lines agree, right? So if I have two curves with the same tangent line, they lift to the same thing. If gamma 3, this orange one, has a different tangent line, so it lifts to something different, right? So we're separating these things according to their jets, right? We're separating these curves according to their derivatives up to reparametrization. So as I've been suggesting this whole time, the symplectification procedure is actually the result of n-4 Cartan prolongations. So we said the symplectification procedure gives a 2n-4 distribution, so n-4 Cartan prolongations is the right number, right? It's not probably clear why this is true at all. It's maybe... well, maybe I'll refrain from commenting. But suffice it to say that this is locally true. The germ that you obtain by taking n-4 Cartan prolongations is exactly the same as the germ that you get when you apply the symplectification procedure. Now the question about when the Tanaka symbols unify, the answer is the n-5th Cartan prolongation. So it's one prolongation short of the symplectification procedure, right? So a generic subset of the n-5th Cartan prolongation of D has constant Tanaka symbol already, again, independent of D, which is given by this subalgebra of the symplectic algebra. Okay, so it's epsilon 2 now living in this G-1, right? And when you prolong again, you get back the entire symplectic algebra here. Now, maybe it'll be useful, I think, both to clarify what's going on and to discuss the non-existence of a Cartan connection, to discuss the sort of the most symmetric case in all those distributions with the same Tanaka symbol as it. So one of the features of the symplectification procedure of Dubrov and Zelenko is that it gives that for n greater than 5, I should say the symplectification procedure is, n greater than 5. I really should have said that at the beginning. I apologize. We're thinking of the dimension of the manifold as greater than 5. The 5-dimensional case was sort of treated by Cartan famously in this 5 variables paper. But I've interrupted myself. So the 2n distribution of maximal class with maximal symmetry algebra, 2n minus one-dimensional symmetries, has GL2 semidirect Heisenberg as its semidirect, or as its symmetry algebra, and all such distributions are locally equivalent. So we have a unique symplectically flat germ, we say, a unique most symmetric germ among rank 2 distributions of maximal class. And this is stronger than Tanaka flatness. So like, this will be the Tanaka flat distribution for a specific Tanaka symbol. Maybe like in the 2, 3, 5, 6 case, it's the parabolic symbol's Tanaka flat distribution. That is the symplectically flat distribution. So let's restrict ourselves just to think about those distribution whose symbol is this subalgebra of the symplectic algebra, because that is the symbol of the symplectically flat distribution. So this is the symbol of the symplectically flat distribution, and again, notice epsilon n minus 3 is in G minus 1, a different one, right? And we have sort of fewer epsilons here. So we've sort of shifted the grading, but when we prolong, we get back the entire symplectic algebra again. And it might not be surprising. Again, we're looking for normal Cartan connections, right? We're looking for G plus invariant normalization conditions. Well, this G plus is like enormous, right? It seems like there's very little hope of finding an invariant normalization condition with such a large G plus, and you would be right if you suspected that. There's no normal Cartan connections here. And the reason I've been pointing out where these epsilons live is because each Cartan prolongation of a distribution with this Tanaka symbol, it's just going to shift the epsilons here. So all that's going to, I guess also the eta. Eta is going to shift by 2, and epsilons are going to shift by 1. So it's just going to change the grading of this same algebra. So if we take the Cartan prolongation once, we now have epsilon n minus 4 in G minus 1, and epsilon n minus 3 is shifted over 1 along with all of the other epsilons. And again, when we take the Tanaka prolongation, we get the entire symplectic symbol. But again, G plus is like far too big, right? This thing is very large, so maybe it's not surprising that there's no normal Cartan connection here. So we can keep doing this, right? We can keep taking Cartan prolongations over and over again until we get to the n minus 6 Cartan prolongation, which looks a lot nicer. We have epsilon 3 in G minus 1, and this one is much smaller for G plus, right? It's 5-dimensional G plus. So you might hope now, surely now we'll have an invariant normalization condition, but you would be wrong. There's no linear invariant normalization condition here. So we can't find a normal Cartan connection. And really the reason we can't is because of this epsilon 2 in G plus. And my hope is kind of to sketch the proof of why there's none here, and epsilon 2 is at its core. That's the reason. That means that if we take one more Cartan prolongation, epsilon 2 shifts into the negative part of G. It's gone from G plus, and now we have a normal Cartan connection, which is good news. This is the one we were looking for, and know that if we took one more Cartan prolongation, the n minus 4th Cartan prolongation would give us the symplectic symbol. Also, maybe it's kind of nice, this works out very nicely, that it's the n minus 5th Cartan prolongation here, because the existence of this Cartan prolongation in the n minus 5th, existence of the Cartan connection in the n minus 5th prolongation also coincides with where the Tanaka symbols unify, right? We take n minus 5 Cartan prolongations, suddenly, no matter what your distribution was, the Tanaka symbol is this, and after n minus 5 prolongations, we have a normal Cartan connection. So these two, the answers to these two questions coincide. So maybe let me sketch why epsilon 2 is sort of an obstruction to the existence of this Cartan connection, why that's the problem for the n minus 6 Cartan prolongation. So there's no normal Cartan connection here. And remember, epsilon 3 was the G negative 1 epsilon here. So epsilon 3 was of weight negative 1, and epsilon 2 is living in the positive part of our Tanaka symbol. So this takes a little bit of representation theory. I hope I can explain it clearly. I try to avoid proving things in talks a lot, but this is an exception, I guess. So suppose that we had a G plus invariant normalization condition n. That is a complement to the image of the co-boundary map, which is invariant under G plus. Well, we have this Cartan subalgebra, H and E being from GL2 here. And this Cartan subalgebra, basically both of these things are invariant under our Cartan subalgebra because n is G plus invariant, right? So we can do weight space decompositions here. Namely, let's see, I think the vertical axis is the E eigenvalues, the E weights, and the horizontal axis is the H weights. I can decompose this cochain complex in terms of those weight spaces, right? So each point here is a weight space, and blue is just the origin. I shouldn't have colored that blue, but blue is not special. Don't worry about the blue one. But n and the image of the co-boundary also decompose into these weight spaces, right? And yes, this is what I just said. The image of the co-boundary and n both decompose into these weight spaces. And in particular, because they decompose into weight spaces, they have to be complementary in each weight space, right? So if I can find some lambda to 0 such that the image of the co-boundary map completely misses lambda to 0, and I can actually, it's this one, this guy, then that entire weight space has to be contained in n, right? Because they have to be complementary. And then I can apply epsilon 2 as a raising operator, which just permutes these weight spaces. And because n is invariant under epsilon 2, when I apply it twice, the image of that map also has to be contained in n, right? But the image of that map actually meets the image of the co-boundary map. So then n would have to meet the co-boundary map non-trivially, and that means that n isn't a normalization condition after all, right? So that is basically the reason that n minus 5 is the very first number of Cartan prolongations you can take where you get a Cartan connection. So there's no normal Cartan connection on the n minus 6th prolongation, but there is on the n minus 5th. And that's the first place the Tanaka symbols unify as well. How am I on time? I think I'm pretty much done. But yeah, thank you very much for listening.
For your fresh talk, you did very well with the dancing.
Thank you.
Right, questions, comments?
So in the theory of rank 2 distribution, there's the following story. So if you just apply this rank 2 distribution in three space context, right? Then do Cartan prolongation, and well, we get angle and so forth. And very soon you see that actually the symbol depends on the point of the Cartan prolongation. Well, there's generically the same symbol, Usasai, but there's also singular symbols. I mean, that's actually known due to the work of Zhytomyr schema boundary. Okay, so you actually can get like there's non-homogeneous. You start with homogeneous, you get non-homogeneous.
Yeah.
Right? The group is in dimensional, so like an open set that is locally homogeneous, but that you have it. But you have to do some prolongation. Is there your number of prolongations related to the same effect?
I don't know the answer to that. I don't know the singular story very well. I've sort of heard it summarized, but I'd have to think about that. Yeah, I'm not sure.
There's a story that like your distributions are homogeneous, you get vertical directions.
Yeah. I've heard the basic outline, but I've never studied that question. I'm not sure the answer. I wish I could help, but I'll think about it. Yeah, I'd like to talk about that. But.
So if you could, I guess, define curvature, or to give you a variance for the original distribution that you studied. I mean, would you prefer to go to the minimal one, or would you would you prefer to do it up at the top because you have this nice GL2 there?
Yeah, that is a great question. I would like to say the minimal one, but
it's no longer going to be GL2. What do you have in your G0, G1?
It's S, so it's the like Y, H, and E invariant. But then also epsilon 1 invariant. That's the additional element there. So you do get some stronger invariance.
Right?
Yeah. Last question. So suppose that the Tanaka symbol stabilizes exactly after n minus 5 Cartan prolongations. is it based on the simplification procedure?
It's pretty much purely algebraic. It does use it a little bit, that there's some integrability property of the distribution itself. Like, you have certain, like, integrable subdistributions from this frame that in the symplectification procedure. So it uses that fact, but it just uses that certain structure functions vanish basically, and then you just quotient out. So you have the inverse, like a recovery from the Cartan prolongation. You have a recovery procedure, and basically you just apply that and the integrability property there. I don't know if that's clear or not, but
Yeah, well, we can I think
Yeah.
I understand it. So
Yeah, sure.
We can discuss this later.
So, any further questions? Doesn't seem to be the case, so let me thank That's all for today.